Hello students. In this video we're going to talk about effective rate. That's also seen quite often as APY, which stands for annual percent yield. We've seen already that when dealing with compound interest, the more often you compound something, even at the same rate, could increase its value. So when we're looking at things in the real world, and we're trying to compare one thing versus another, it's important to have a way to standardize what the rate is as a matter of comparison. And so because of that, we've come up with what we call the effective rate, or annual percent yield, which says no matter how often we compound it, at the end of the year, how much, by what percentage, did that investment grow? So let's take a look at it. So first off, we have two different types of problems, as we've seen so far. We've got where things are compounded finitely, like monthly, quarterly, daily, annually, etc. And we've got compounded continuously. Each one is handled slightly differently, just as they are with the regular compound interest problems. If it's finitely, we have a couple of different methods for tackling how to find this rate. So we have a formula, and if you notice this formula, the APY, that annual percent yield, it has a look that's very similar to the actual compound interest formula itself. We're used to P times 1 plus R over M to the MT power, right? Well, since we're talking about a single year, that T is 1, so we don't need it. And since we're only talking about rate of growth, it doesn't matter how much we invest, it's still going to grow at the same rate, so we don't have to worry about the P. The thing that does matter, though, is this 1, since this is a rate, that rate is a multiplier of our original balance, so it still technically includes our original balance. So we subtract 1 representing 100%, 100% of our original balance. We get rid of that, and what's left over is the effective rate. Okay, so that's the basis for the formula, and the same is true for the continuously one. We also can use the TI-83 or 84 calculator to find it using the TVM solver, which we use for the other problems, as well as the EFF command, and I'll show you how to do both in our example below. So let's take a look at that. For our example, we're talking about a new bank is offering a savings account with 3% compounded quarterly. Your current bank offers 2.99% compounded continuously. Which is the better deal? Okay, so this is a good example where we're actually given two different percentages, two different rates, compounded at two different periods, and we need to be able to compare them to say which in the end, in the long run, will be more effective. Well, the first bank, the one that's new, is offering a quarterly investment. That's a finite one. So we can use any of the methodologies we talked about before. Let's start with the formula. The formula goes as normal. We start plugging in values. We do have to be careful, though, with this R. If you notice right here, I've got it plugged in as 0.03 instead of 3%, usually, and almost entirely exclusively for finance. Whenever you see a rate or something as a percentage, you don't actually plug it in as a percentage. You have to convert it to a decimal first. Okay, so this is still true. So we've plugged in 0.03 in for R, 4 because quarterly is 4 times per year. That's what the M stands for. Let's plug this in the calculator and see what kind of numbers we get. So we've got 1 plus, and you notice I started with parentheses here. I like to be redundant with my parentheses just to make sure it's doing exactly what I tell it to. So 1 plus 0.03 over 4. I put the fraction in parentheses and then close it so that everything on the inside from my original problem is actually all in parentheses. That will be raised to the fourth, and subtract 1, and I can see that the rate as a decimal of growth is 0.030339. So let's multiply this by 100 to find out what our percentage is. Okay, so 3.03391 9%. All right, that's plenty of decimal places, probably more than we need in the long run, but better be safe than sorry, have some extras. Okay. Now let's look how we would figure that out if we were to use the TVM solver in the same kind of way. So earlier, when I was talking about the formula, it said it didn't matter what we started with. It doesn't. It doesn't matter what value we start with. The rate of increase is still the same. But in our TVM solver, we have to start with something. Okay, and so what I have done is I've put in quarterly for that 3%. I'm going to put in a single dollar. Okay, a single dollar, and the reason why is because for every penny I earn off of a dollar, it's a 1% increase. So the however many decimals, however many cents extra that I earn is exactly the percentage or the amount of the rate of increase, of that effective rate that we're looking for. So I'm going to use $1 specifically. I could use anything, but it's a lot easier for us to use the $1. I don't have any payments. We're going to let the $1 sit and see how fast it grows across the year with 4 compounds payments per year, quarterly. Once we find a future value, we notice that we still have the $1. Well, again, just like before when we said removing that original amount, I put in $1 originally, so if I were to take this, and you can actually do minor operations even within the TVM solver, I've got this value. If at the end of it, I just subtract 1 to get rid of the original dollar I put in, then I've got exactly what we see up here on our previous answer, except for that's the rate. That's the decimal. We want to turn it into percentage, so we'll go back to the end here, and we will multiply by 100. And we'll see that we get exactly the same thing that we got before. Okay, now for the finitely, the winds up being the easiest way to do it, is the last way I'm going to show you, is the effective rate. There's a command already built in doing that, so it's under apps, just like the TVM solver, but instead of it, we're going to keep going down. We're going to go all the way down to C, where EFF command is, EFF, and from here it takes 2 inputs. The first input is the percentage, actually a percentage of the investment. So for us was 3%, so just 3, not 0.03, not the decimal, just the percent. And then comma, and then the second input is the number of times per year that we're going to compound it. So for us, since we're doing it quarterly, it's 4. And we get the same answer we got before, exactly. All 3 methods all work. Here's just a way to do them. Okay. So let's look at that in comparison to our continuously. Which is the better deal? That's still our goal, right? So our interest, our compound interest for continuously, e to the the RT, again, we don't care about P or T because we're looking at 1 year, and the rate isn't affected by how much we invest. The rate is still the same. So we're going to go through the same strategy. It just uses the other base, the continuous formula base, instead of the compound finitely base. We're going to plug in e to the 0.0299. Remember, 2.99% converted to a decimal. Let's clear this out. Let's plug it in and see what we got. E to the 0.0299 minus 1. And in this case, let's multiply this by 100 to get back to our percentage. And we see that our percentage is 3.0351. Well, we don't have to go any further. We can already, let's just round this off at 515%. And we can see really clearly right away that even though the 2.99% started off smaller than the 3%, just compounding it more often in the end wound up having a little bit more yield than the compounded quarterly.